our senior ASC capstone project, our team decided to create a product that could also benefit people that needed an emergency source of energy to easily charge their phone, while also promoting a healthy lifestyle. Throughout weeks of consideration, we settled with the idea of Green Kicks, fully functioning shoes that are capable of charging a portable battery by simply having someone walk in them that were comfortable and easy enough to wear on a daily basis.
Our product, Green Kicks, was based on the concept of piezoelectricity and piezoelectric crystals' ability to incorporate the body weight of the user to generate electricity. The body weight of each user and the force that arises from each step pressurizes the crystals, generating electricity in our shoe. Through walking or running in the shoe, your body weight and your body's motion can generate a renewable source of energy for your shoe. We will go into specific details of the science behind the crystals later in the video.
Alright, so let me break down piezoelectricity. In a piezoelectric material, its charge is neutral and the protons and electrons cancel each other out. But if you apply pressure to the material, you force the charges out of balance. Now the net, positive, and negative charges appear on opposite faces of the material. So, by squeezing the material, you've produced a voltage across its opposite faces. We created piezoelectric crystals to create this process, but other materials like piezoelectric ceramics will also produce a voltage. How to make these crystals? You start off with weighing 7 ounces of cream of tartar. Now, take the cream of tartar and mix it with 1 cup of distilled water in a Pyrex cup. Fill a pot with water and place the Pyrex cup into the pot. Heat the water on the stove until it reaches 180 degrees Fahrenheit. This method will evenly distribute heat throughout the mixture. The mixture should be simmering, not boiling with the water. Now, add a teaspoon at a time of soda ash and mix until it is dissolved. About an hour of adding soda ash, the mixture will stop bubbling and turn clear. Allow the mixture to cool and then pour it through a coffee filter. It should take about another hour to filter through. Afterwards, refrigerate the mixture overnight and you'll wake up to piezoelectric crystals.
To test if the crystals we made from home worked, we placed copper sheets on both sides of the crystals and used a voltage meter to check if we were generating electricity. While Erin used her body weight to pressure the crystals on top of the lab table, Joyce measured the voltage being generated with the help of Mr. Avis. We were able to successfully record an average of 11.9 volts being generated with each push. The entire point of this test was to record the evidence that these crystals were actually generating electricity.
Before we could even start creating the shoe, we needed to research what exactly piezoelectricity was and how it could be applied to our project. First, we had to understand the mathematical properties of piezoelectricity. Piezoelectricity is the combined effect of the linear electric behavior of the material and Hooke's law for linear elastic materials. The linear electrical behavior is described as the equation D equals epsilon times E, where D is the electric charge density displacement, epsilon is the permittivity, or also known as the measure of resistance, and E is the electric field strength. Hooke's law for linear elastic materials is T equals big S times small s. Big S is the strain, which is the measure of deformation, representing the displacement between particles in the body relative to a reference length. Small s is the flexibility, and T is stress applied on the material. In relation to Hooke's law, we are able to generate the equation above.
We wanted to test 2 designs of the shoe before selecting one for our final product. One shoe was going to be based on store-bought piezoelectric discs, while the other was going to be based on homemade Rochelle salts. Both tests were done on the same type of shoe that we bought from the same store, and the weights of the user was the same because both of them were done by Sydney, pressurizing both types of the piezoelectric crystals in the same type of manner. For our first design, we decided to use 27mm piezo disc elements with 4-inch leads. Acoustic pickup cigar box, guitar CBG. Design details. There were a total of 14 discs used on the makeshift sole, 8 on the ball of the shoe and 6 on the heel. The number of discs had to be split between the top and bottom sides of the sole as well, making a total of 7 discs on the top and 7 on the bottom. This allowed for maximum amount of energy to be created with the small surface we were given to work with. This simple structure also allowed for an easy wiring technique. The positive and negative wires of one disc were connected to the corresponding positive and negative banks of the adjacent disc. This made the wiring of the discs uniform, making designs clear and problems easy to fix. For soldering and gluing, we soldered the wires to each other into the diode. We glued the discs onto the sole. With the cardboard and foam sole in efforts to increase the eventual voltage produced from the piezoelectric discs, we placed a small, square piece of cardboard onto the center of the disc. This would allow less travel distance between the foam sole, which acts as a comfort barrier between the sole with the discs and the person's foot, and allows for a greater pressure to be applied. This extra distance made all the difference when testing for a decent voltage reading.
Our next step was wiring the bridge rectifier. To do this, we wired the piezo element wires to the bridge diode according to the circuit diagram. Since the current is AC, the position of the wires are interchangeable as long as they connect to the correct diodes in the diagram. We then stripped the USB charge cable that came with our battery pack to reveal the internal wires. For the purpose of this project, we will only need the red and black wires, so we stripped those also. We then twisted the frayed wire strands of each wire and welded them with a soldering iron. Then we soldered the wires to the bridge diode accordingly. We made sure to check the polarity since DC voltage has positive and negative terminals. Lastly, we hot glued the connections to prevent the wires from breaking off.
This shoe design was fairly simple to make as we had the diodes and store-bought piezoelectric elements ready at hand. We were able to make the shoe in about 2 to 3 meetings.
So some of the cons of our project was that we were able to see that our design could charge the battery, but after a few runs and walks on the design, the cardboard sole and the wires were already becoming weak and withered, creating a break in the energy flowing into the battery. The sole was not strong enough to support the full body weight of someone for a sustainable amount of time. We learned that to create a shoe that was worthy of being manufactured in factories and of having the chance of being sold to manufacturers, we had to create a design that incorporated a stronger sole that could sustain the movement and weight of a normal-sized person. Cardboard and foam were out of the question, so we decided to look for other alternatives. We decided to use 3D printing for our next design, with pre-made slots for homemade crystals to test if this sole would be more sturdy and sustainable.
The main goal of the second design was to fix the main problem of the first design, energy output. We decided to fix this in 2 ways, the first being making our own version of a piezoelectric disc. To do this, we made the crystals ourselves, using the process that was described earlier. The hope in doing this was that we would make a bigger disc that we would eventually call a piezoelectric plate. Only 2 of the plates would go onto the sole due to the increased size, but the crystals would generate more electricity because pressure is being applied to the entire plate as opposed to the first design. The second way we tried to increase energy output was by 3D printing a sole for the piezoelectric plates to fit in. This design came about because the plates were made too large to fit on the sole for the person that was wearing the shoe to have their foot comfortably fit inside. So we decided to make an online model of the entire bottom half of the shoe for the plates to fit in addition to a hole for the battery. Although the 3D printed sole was not what we went with in the final product, we used the design of the prototype in the final shoe.
One was the stiffness of the sole. Because it was 3D printed with a non-flexible fabric, the sole we printed was not able to move with a foot like other shoes on the market are. Either rubber or a more flexible plastic would be needed to fully incorporate this 3D design into our product, but we simply did not have the resources or ways of getting them in the time frame we were given.
We learned that the design we had for the printed sole was the best design for our shoe. The holes allow the plates to fit comfortably in the sole while still getting the maximized energy output from the crystals. This solves our problem from design 1, so we implemented that into our final design. We also learned that hard plastic is probably not the best material to be the sole of a shoe because it's uncomfortable. In light of this discovery, we proceeded with the design and the sole of the shoe we were already using from our design 2 and a completely new material for the sole.
In our shoe, we had to somehow create our own piezoelectric discs using the crystals we already made. In order for the Rochelle salts to generate electricity, we decided to use copper as the conductor. We cut 2 holes in the heel and the midfoot region of the sole and placed a sheet of copper inside. Then we added the crystals and covered it with another sheet of copper. Next, we developed a process for wiring the piezoelectric plates to the power bank. We did this by soldering 2 pieces of wire to each piezoelectric plate. One wire was attached on the top and the other onto the bottom. These wires would all be connected to a diode, which is a circuit that does not change the polarity of the input. We then attached the wires to the power bank cable to connect the whole system together.
We calculated that each step generates 0.16 volts. We derived this data by measuring half of the crystals in one plate and discovered that an average of 40 millivolts were being generated from each pressurized squeeze from our body weight. This replicates the motion of our body weight in the shoe and the resulting amounts of volts to generate. We measured this data through a voltmeter. Additionally, since our final design contains 4 times the amount of crystals and copper plating, we multiplied 40 millivolts by 4 and converted that into 0.16 volts.
An iPhone requires 694.4 volts to fully charge. Each step generates 0.16 volts, so when you divide the number of volts required by the number of volts created by each step, that means that it takes 4,338 steps to fully charge an iPhone, or about 2 miles for the average person.